All right, so what you do is we're gonna put the light, there's a small little slit back here, we're gonna put the light right next to it. The light's gonna come in and it's going to reflect onto here. And so if you look through this eyepiece, you'll see very distinct light along here. All right, who would like to come over and see this heat spectrum? We need some light, but not too much light. Just don't touch the thing that's humming. So you look at it, you sort of look to the right, and you see lines?
Yeah.
So as the electron basically energy puts the electron in a higher orbit, then the electron comes back down to the lower orbit, and that difference in energy corresponds to, if you knew that difference in energy, you then can use HF to figure out what the frequency of light is, and these happen to be falling into the visible spectrum.
Little thing, but you can see them.
Oh. Is that the wrong way on that one?
It's too bright now.
Too bright?
I couldn't see. Yeah, just see like the. Yeah.
He's blind now.
No, I meant like the light coming from the side. You couldn't see the.
All right, so we need, can somebody kill that light? Please. All right, so. And that is not easy to see. Try it this way. All right, you can see the green. There's a green line there. So we did this earlier.
I didn't see like a violet
I
one,
saw
a
green.
green.
Yeah, I saw green for sure.
And there was a violet one. So that one's up there. All right. You should be able to see a green line. There's also a blur from the ambient light. There's a green line there and a purple line are the ones that I'm seeing. Did you see it?
I guess I saw it.
There's the yellow one, the green one, violet,
All right, so you're seeing it?
Yeah. and then, yeah. The violet, the green, and like the yellow one.
Yeah, I saw it.
Okay.
I can see them on both sides too.
All right. Maybe I just need to lock some of the light. Now, each atom is gonna have a unique signature about what lights can be seen, and also the intensity of it, and there's various websites out there where you can look up the frequency and it gives you a relative intensity. So from this, you can then start to put together, you see a distant star, what is the frequencies we're seeing? Oh, it's made up of these.
Oh, wow.
And there was, I think some woman from, she was a Harvard professor in the 20s, if I recall correctly, who basically went through all the laborious task of actually doing this by hand.
Yeah, I see a few colors. It's not loud at the most.
Is it a lot of the most?
Yeah.
Huh.
I think the orange
Yeah,
one.
I see line,
is
but I
about
think it's
some
because of the
green.
white glasses. Yeah, I see
Probably.
reflective
Did
coating.
you see them on both sides or just one side?
It reflects blue light, so I didn't see any blue light.
Okay, yeah. Okay, you have the thing on the box.
It's like I sent them in here like this reflective.
Oh,
coating.
Yeah, I know what you're talking about.
I remember something similar like that in chemistry.
Yeah, yeah, oh, yeah, yeah, yeah.
Don't we just see like that?
See, you're gonna
light,
really want that, I think.
green, yellow.
I have studied this back in high school. I kind of forgot.
Trevor, do you want to see it again?
I think it was like,
It's pretty cool
I
because
think it was Moore's model. Or
Yeah,
that,
yeah,
or
yeah.
different thing.
As a board model.
like there's Maxwell's also graphs
Yeah.
and stuff.
I don't remember any of that. Like,
I
just don't like that sound from.
Probably not even cheap.
Exactly.
No, 2 years.
Is that what you guys
Chem 1, yeah. Chem 2.
Now, there were numbers there that I don't know if you could have seen, but there were numbers there that, where you could then pinpoint the wavelength. Those numbers are in 10 to the negative 7th meters, I believe. And so then you can start recording and being able to identify, and which is a lab that I do with the 133 group, because they're specifically studying optics. And this falls into it.
Wait, 132 is?
133.
Oh, that's pretty cool. I might have to take that class during the summer.
Engineering tech.
You teach it?
Not this summer. I've done it the last 3 springs.
Was that for the MET program?
It's the, of the class, there's 5 in the class, 4 of them are engineering tech, planning to get jobs right after this, and one's planning to go to the 4-year school.
Yeah, that's, I think that's the program after,
Okay, all right.
that's all.
Don? Yeah, sorry. Mine went off on a tangent just then. All right, so the discrete spectra aren't accounted for. And so enter Niels Bohr. And I recognize we are really low on time here. Now, the thinking of that last question there, number 7, why do electrons crash into the nucleus? The electron is zipping around a nucleus in the nice planetary orbit. We now know it's more sophisticated than that, but for right now, the electron's going around the nucleus. And so the electric field is constantly changing, which means that electromagnetic radiation should be produced as this electron orbits. And because the electron is orbiting and giving off energy, it should be losing energy, and therefore the electron, as it loses energy, should eventually crash into the nucleus. But it doesn't. So Niels Bohr made a couple of assumptions. Well, one, that wasn't the assumption, they knew at this point that atoms were small. I know that's a shock for you, but he quantized, in other words, assumed that there were very discrete levels here, that not just any old orbit would work, but he assumed that the angular momentum was proportional to the frequency. No, was proportional to actually that constant of proportionality. It's equal to some number times that. Technically h bar. H bar is just h divided by 2 pi. Oh, I never actually talked about h This is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And with this assumption, you basically, you come up with energy is proportional to 1 over n squared, and that the orbital radius is equal to some number times n. Nope, sorry, n squared. If you've had chemistry, they talk about the quantum numbers. N equals 1, so it's N, L, M sub L, and S, the 4 quantum numbers. This is the first quantum number right here. N is equal to 1 is the first orbital level. Basically hydrogen, helium, that's where those electrons hang out. N is equal to 2, we're now at the next orbital level. So we're now dealing with the outer electrons of row 2, and so on. The difference, yeah. And in 1 minute, and then, I guess the last bit, we aren't gonna get to walking through walls. But the last thing that we'll do is the thing that Prince Louis de Broglie, Louis Victor Prince de Broglie, that name that I'm sort of guttural on, somebody who actually looked it up, how to pronounce it, I believe it is de Broglie, it's Broglie. My French accent has never been anywhere close to spot on, but I think it's something like that. He comes up with this crazy idea. Now, the fact that he's royalty probably doesn't hurt, but he came up with this crazy idea and said, well, if photons can behave like particles, can particles behave like waves? So he speculates that all things have a wavelength. And again, Planck's constant shows up yet again, and obviously I'm not deriving this one, but this is the Broglie wavelength, h divided by the momentum. So if you think about, we have this number right here, 6.626 times 10 to the negative 34th joule seconds, divided by momentum. Well, if I got a 1 kilogram object moving at 1 meter per second, I have 1 kilogram meter per second. That's an incredibly tiny wavelength. This is beyond what we can measure right now. But if you start dealing with electrons zipping along, then we start dealing with, well, the mass of an electron is on the order of 10 to the negative 31st. We start dealing with wavelengths that become manageable when we start dealing with small objects. And then the Davison-Germer experiment, which got Davison a Nobel Prize, but not Germer, is they took electrons and they shot electrons at a double slit. And so the electron would go through, and you'd get when it hit the other side, there'd be a scintillation point, there'd be a spot that the electron hit. And then they do it again, and they do it again. And electrons are hitting all over the place here. And then if you look at where the electrons are hitting, there's a whole bunch that hit right there in the middle, and then there's some that hit here, and then there, and you got the dead spots where no electrons hit for the most part, and you basically get the wave pattern. And then they thought, well, I'm shooting an electron one at a time. I shoot an electron, let's put an observer right here, let's put a detector right there to figure out which slit it's going through. And as soon as they did that, that goes away, and you get a bunch of electrons here, a bunch of electrons here, like a particle. The mere act of observation switches this from a wave into a particle. And that is the mystery of where we're going to leave it. And Germer did not get the Nobel Prize because he just happened to be the grad student at that time. One grad student finished, went off somewhere else. He was the next one to get in, so he was not there for the full thing.
Do you want me
If you can turn that off,
to hit pause or?
either stop or pause, either.